Chapter 5 Phase Diagrams of Metals. There are 3 topics. First, Gibbs phase rule. To this, I will give you the introduction to phase diagram and to show you how Gibbs phase rule is related to the construction of the phase diagram. Then on the next topic, we will concentrate on different types of boundary phase diagrams, including isomorphous, eutectic, eutectoid, peritectic, peritectoid, and monotectic types of boundary phase diagram. Finally, and very important, it is the iron and iron carbide phase diagram that I will give you the details on the phase calculation and interpretation. For the learning outcomes of this chapter, first, students will be able to classify phase transformation reactions of the alloy systems provided. Second, to identify phases and composition present in the boundary phase diagrams of various alloys. And third, you'll be able to calculate the amount of phases according to the given composition and temperature. And finally, to explain microstructure property evolution according to the iron-iron carbide phase diagram. First, I will give you the definition of phase before we get on to Gibbs phase rule. And here is the introduction to phase diagram. The definition of phase is a physically homogeneous and distinct portion of a material system. And if you have a look onto the picture below here, you will see more clearly about phases. So the picture on your right contains 2 phases, which is in the gaseous state, and the water, which is in the liquid state. But then if you look onto the picture to the left, you can see that there are 2 ice cubes, which are in the solid state. So now you have 3 phases overall, which are the vapor, water, and ice. So another definition of phase is a region in a thermodynamic system. That is, physical properties such as density, index of refraction, magnetization, and chemical composition of a material are essentially uniform. So this region might be vapor, water, and ice that show different physical properties. Also, the phase is the region that possesses homogeneous or uniform physical and chemical characteristics. First, when you have a look onto the picture, and when you mix ethanol with water, since ethanol is soluble in water, so you can see just one phase that is incomplete soluble. And for the second example, when you mix phenol into water, you can see now 2 phases because phenol is partially soluble into water. Down here you can have the mixture of water and phenol, but above here you can see a different phase of phenol with small amount of water. So this system contains 2 phases that are in partial soluble. So the last example, when you mix mercury into water, you can now clearly see 2 phases that are complete insoluble to each other. So you can see that when we see homogeneous or uniform region, we can recognize that it is one phase. But if not, like these 2 examples, so we can classify different regions as different phases as well. And this we can see by our naked eyes. But for the metallic materials, there are normally more than one phase in the alloy, and that we cannot see by our naked eyes. We have to use the device such as optical microscope to investigate different phases within the alloy, so we can understand how it behaves in service condition that we designed it for. So now let's get to the Gibbs phase rule. The Gibbs phase rule is general principle that governs the systems in the thermodynamic equilibrium. For example, if you look onto this picture, showing the temperature of one component, which is H2O in degrees Celsius, and on the y-axis is the pressure of the same component in the unit of torr. And if we're talking about within the region, within the temperature of 100 Celsius and the pressure of 760 torr, we can see 3 different phases over here: solid, liquid, and vapor. Also, there are 2 lines that separate 3 different phases. The first one is lying over here, which is the vaporization line that separates 2 different phases, which are the liquid and the vapor. Another line here is the freezing line that separates the solid and the liquid. And if you can notice, over here is the triple point at 0.01 Celsius, that the 3 phases of the solid, liquid, and vapor can stay together. So now I will introduce you the Gibbs phase rule. P plus F equals C plus 2, where P is the number of phases, C is the number of components, and F is the degree of freedom. For example, at the triple point, the solid liquid vapor point, if you recall the Gibbs phase rule, which is P plus F equals C plus 2. So over here there are three phases of solid, liquid, and vapor. And then you recognize that it's just one component of H2O. So C becomes 1. To this point, we have F equals 0, which means it's the 0 degree of freedom. That means you can't move from this point in order to get three phases stay together. And that is how F works as the degree of freedom. You have no chance to move to stay in three phases. And for the second example, on the solid-liquid boundary, which is over here, along the vaporization line. And now you can recognize that there are two phases, the liquid and the vapor. So there are two phases over here, and still one component of H2O. At this point, we have F equals 1, so we have 1 degree of freedom. So it means we can move along the line in order to stay two phases altogether. That is in solid-liquid boundary or the melting line. And for the last example, in the area of each phase, in the solid, in the liquid, and the vapor. At this point, we have just one phase and still one component. So now we have 2 degrees of freedom that you can move in the X and Y direction, and you can stay in one phase. So in the equilibrium material system, the pressure is generally constant, that is 1 atmosphere. And therefore, the Gibbs phase rule becomes P plus F equals C plus 1, as number 2 is replaced by number 1. And for the binary mixtures of two chemically independent components, for example, like we mix metal A and B together to make an alloy. So the component of C now becomes 2, so that F becomes 4 minus P. And that is when we're talking about the Gibbs phase rule with varied temperature and pressure. And the picture over here showing the binary mixture of two components, which are the copper and the nickel, on the weight basis. And in this condition, we exclude the variation of pressure, assuming on the atmospheric condition. So we have the variation of composition, 100% of copper over here. And then we mix nickel at 10, 20, 30, 40, and so on, up to 90% of nickel, and become 100% of nickel on your right hand side. And on the y-axis, we have the variation of temperature from below the melting point of copper and up to above the melting point of nickel. There are two lines over here as well that separate the liquid phase and the solid phase. The solid phase here is the solid solution, namely the alpha phase, which means that the copper and the nickel can mix together and appear just one phase. And I will talk about this later. So we have the liquid phase up there and the solid phase down here. And you can recognize the area over here between the two regions that contains two phases, which are the liquid and the alpha solid solution. Point A, we have just one component of copper according to its composition. And point A on temperature line is the melting point of copper. So that means we have two phases over here, one that is solid and one that is liquid. So when we get back to the Gibbs phase rule over here, which is P plus F equals C plus 1, we're replacing P with two phases of liquid and solid, and replace C as one component of copper. Then we come out with 0 degree of freedom, which means that we can't move from this point, that we can still have two phases. Now let's consider at point B, that is the region that contains two phases of liquid and the alpha solid solution. So according to the Gibbs phase rules, we still have two phases over here. But then in the B region, we have two components of copper and nickel. So over here you have 1 degree of freedom to change either the composition or the temperature to stay two phases. And the last example is at point C. That might be either in the area of solid solution or in the liquid. At point C, we have just one phase, that is over here, and two components. So we come out with 2 degrees of freedom. Over here, we can change both composition and temperature to stay in one phase. And when the metal is alloyed, it means when you put one type of metal into another one. For example, when you put 10 weight % of nickel mixed into the copper, and that is copper alloyed. But then on the other hand, when you put 10% of copper into nickel, it is now nickel alloy. Or it means the nickel is alloyed with 10% copper. So when the metal is alloyed, there are different ways solid solution can be formed. If I give you here, the green atom is from the metal A, and the pink atom here is from the metal B. So within this first picture, we now have the solid solution. That means the solution is in the solid state as you put metal B into metal A. And atoms of metal A are more than atoms of metal B. So metal A atoms are the solvent atoms, and that metal B atoms are the solid atoms. And you can see that the atoms are arranged in pretty much an ordered manner. And it is that metal A atoms are replaced by metal B atoms. So now we have the substitutional solid solution, that the atoms are arranged in order for one atom to replace another atom. First, they ought to have pretty much the same size of atoms, so that the solid atom can fit into the space quite comfortably with less constraint and distortion. Another example here on your left is also the substitutional solid solution. But now the solid atoms of metal B replace the solvent atom of metal A randomly, not in the order manner as in the previous example. So now we have this ordered substitutional solid solution. And these two examples will happen as metal A and metal B have similar atomic size or not much difference within 15%. The last example is the interstitial solid solution. And when the solid atom as appear in the tiny red atoms over here, that does not replace the host atom or the solvent atom of metal A over here, but with its tiny size of atom, it can fit into the space between the host atom. And that's why it's called interstitial atom. And these interstitial atoms fit into the space randomly. So now we have this ordered interstitial solid solution. It is the solution in the solid state that the interstitial atom can fit into the space disorderly. Within this type of solid solution, two types of atoms are in different size. And for a given chemical composition, different arrangement of atoms of a mixture results in different phases that are related to different properties. And for the example in the picture over here, I will give you the example of two phases, which are phase 1 and phase 2. In the big blue square, here's in the phase 1 that the pink atoms replacing the size of the green atoms. So phase 1 is disordered substitutional solid solution phase. And now if we move to the next region of phase 2, the pink atoms replacing the green atoms in order, even though there are two types of atoms same as in the previous phase. But within this region, the amount of the solid atoms or the pink atoms are much higher than in the previous case. Moreover, they are arranged in order, so we can see clearly that phase 2 has different atomic arrangement in comparison of the arrangement of atoms in phase 1. The picture on your right hand side here shows a photomicrograph of a palladic steel, and this is the optical micrograph that we can see different phases highlighted in different shades of gray. And the steel is the ferrous alloy, that is, the iron is alloyed by a small amount of carbon that we call steel. Within this palladic structure or polite, we have the brighter area of the ferrite that contain very small amount of carbon, for example up to 0.002% of carbon dissolved in the iron matrix. It is an interstitial solid solution because the carbon atom is very small and can fit comfortably into the space in the iron lattice. On the other hand, the darker layer over here is the cementite that is not solid solution but is the metallic compound of the iron carbide that contains the carbon up to 6.67%, and hence this cementite is normally hard and brittle. So the whole structure of pearlite containing alternate layers of soft pearlite and hard cementite shows kind of distinct properties such as strength and toughness, and this is due to the contribution of two phases over here.